All right. Here we are with a little DRAT COVID edition. I had a conversation with Lena this morning about binary data encoding. I thought maybe that's a more relevant and interesting topic than assembly language programming at the moment. So we're going to talk about data encoding here. I think it's a pretty easy thing to overlook and not think too much about when you're writing software. But a ton of time and effort goes into making sure that computers are talking to each other in a intelligible way. That means making sure that the data that's passing from one to another, that it's in an understood format. And that everyone sort of agrees on the encoding that information passes through. So, we talked about HTTP a while back, and we sort of touched on encoding a little bit there, but it's super important. One of the big sort of one of the most important sort of aspects of like an HTTP request is knowing the format of the request body or the response body, so that you can interpret it correctly. So there's lots of different ways that data is encoded, and this is and so I'll go through a few different sort of kinds of encoding, and also dig into like some like little weird, sometimes surprising things about encoding data. So you've probably all seen something like this. You like open up a text file and you see some like garbled garbage. Usually what that means, or often what that means, is that the data is encoded as binary, and that that binary encoding, some of those bytes in the file look like text, or can be interpreted as text, but some of them can't really. So this might be something that you sort of stumble across, and you might wonder, okay, what is this? What is this data? So one like really important tool, a useful tool, is a hex editor. So a hex editor allows you to look at the bytes in some piece of data, say a file, and look at the actual like byte values to sort of like begin to piece together what you're looking at. So so here, this still doesn't look particularly sensible, but if you know something about how it was encoded, then you can start to actually like pull out data and sort of make sense of what's in here. So I happen to know what this was, how this was encoded. So I'm going to run this this code for decoding it here. This is a Python program. It uses the struct package, which is, which I have the documentation for here, which basically is a way in Python to interpret mostly binary data and to sort of like pull that into Python data structures. So, you know, taking raw binary data, interpreting it, and then the struct package actually like will, you know, create like integers or strings or other kinds of data structures in Python that are sort of like decoded versions of what you are unpacking. So so what I'm doing is actually, oh, I'm actually not using, I used struct to pack this file, but I'm not actually using struct to unpack it. I'm basically just going to read in the bytes from the file, and then I'm going to do this simple transformation on them, like an XOR operation, and I'm going to print out the data that comes out. So if we run this thing, happy birthday, Matt. Matt's not here. What an asshole. He's not even here.
That's so sad.
It's so sad. I made this whole presentation just to tell him happy birthday, and he's not even here. That's fine.
Is it his birthday?
It's Matt's birthday. That's not all that I wanted to talk about, so we'll just move on from that. But basically, you know, this sort of demonstrates a little bit about like how well, actually, let me actually show you what the encoding looks like. So so for each character in the string happy birthday, Matt, I am going to write a single byte, which is the you know, packed version of the character, or actually the integer of you know, conversion of this character, XOR'd against X 0x55, so some arbitrary number. So so all that I did was basically take each character in the string happy birthday, interpret it as a byte, which is this value, and then XOR it with this value, and then pack that as an unsigned character byte value into the file, and that's what you get here. So so that's an example, a simple example of an encoding. I wanted to also show you some other kinds of encoding. So I've got a text file here. I'm going to save it, and I am going to, I'm actually going to save it as UTF-8. Let's see, where'd that go? I'm going to open it. Yes, trust myself. And I'm going to open it in my hex editor. Okay, so that's what I meant to do. So you can see here that this text blah blah got encoded. It looks like text if you know, sort of interpret it that way. Note that this last character here is actually a carriage return, or a new line, I guess. The character 0A, and so that's, you know, not sort of that's just another byte in the file. The rest of the characters, you know, each one is has its own ordinal value, and the hex editor is interpreting this. Most likely it's sort of interpreting, I don't know, maybe UTF-8 or something like that. But if we save this thing as a save, how do I, oh God. Okay, we'll make a new file. We will save this thing as a different encoding. So let's try, let's try Japanese. So I'm going to save that in a different encoding, Japanese encoding. We'll see what that looks like. Oh, does it actually look the same? That's boring. Yeah, it actually looks the same. I wonder if there are other encodings I can save as that are more interesting. Save. Oh, maybe Shift.js I think might be more interesting. No, kind of looks the same too. Yeah, okay. Bad example, but generally I think that most encodings, most text encodings treat the Latin alphabet, at least, the same. So, so you know, the characters that are or a lot of text encodings have the Latin alphabet as part of like the or supported as part of the encoding. However, if I put something in here like an emoji or let's say like maybe like French, let's do translate. And let's say, happy birthday, Matt. And we put it into Sanskrit. All right. So we're going to copy this and we're going to put it into our text editor. The text editor, actually, let's do a new one. The text editor is going to interpret this as whatever encoding I pasted in, probably UTF-8, because most shit is UTF-8. If I try to save this in a weird encoding, like, oh, it's not even going to let me. It's not even going to let me because you asshole. It won't let me because it knows there's characters that it won't be able to encode. So thank you, Apple, for saving me all that trouble. But basically, it knows that there are characters in there that can't be encoded in that encoding, and so it's not letting me actually save it. We could do it a different way. We could, well, we could write it in some Python code, but actually, maybe it's interesting to look at UTF-16. So let's save this like that. All right, so we got another file here. Again, this VS Code editor is showing this in UTF, or actually it's interpreting it properly. So it's doing something smart here to know what the encoding is. And if I look at this in a hex editor, it's going to look quite different from what we saw before. So you can see like now the decoded text, which I'm guessing over here, the decoded text is only looking at like probably ASCII character set, which is like, you know, some subset of 10 to 100, the bytes 10 to 100. And it's not seeing any characters that it really recognizes. And you can see actually all of these values are pretty big. So they're like in the upper half of the byte. And so none of those are valid ASCII characters. The other thing that you can see is actually, here we go. So it's showing you what this, it's showing you, let's see. Actually, that's interesting. I don't know why. Maybe big endian. Yeah, there. No. Does that look like that? I don't know. Anyway, it's trying to interpret these as UTF-8 characters, and they are, well, some of them are valid UTF-8 characters. Some of them are like junk. You see these like question mark thingies that means that like it doesn't know what that character is. But we know that these are UTF-16 characters. And so each 2 bytes corresponds to a single character. I don't know why this thing is not actually interpreting these, why this hex editor doesn't seem to be working here, but in any event, you can kind of see like, you know, this is what a different text encoding would look like. Interestingly, these 4 characters are not 16-bit, which is a little bit weird. I feel like I did something weird with the text.
I thought Google Translate just didn't bother changing mat. It left it using the Latin alphabet.
So Google Translate did. So that's right. And this is probably UTF-8, right? So this text right here that I copied is probably UTF-8, but I copied this into, well, let's try a new file actually. Let me get rid of some of these. I copied it into a new file, and it probably pasted it as UTF-8. But then I in the text editor, I saved it as UTF-16. So I thought that see, I chose UTF-16, and I thought that would re-encode it, re-encode the text that I had entered as UTF-16. But I don't believe that these are UTF-16 characters because, well, they're not 16-bit. But maybe UTF-16 has some short, like it actually has some, I don't know. I thought that UTF-16 was actually affixed with like every single character is 16 bits, but I could be wrong about that. Let's see. Yeah, that's better. Okay, so now let's see if it's big endian. That still doesn't look like the right, well, maybe it is the right characters. I don't know. But in any case, I think that this is now UTF-16. Although, Why is this thing being so weird? Then I don't know why Matt isn't. It's just weird. It's just weird. There's some weird shit going on with this text editor. But anyway, all of that to say, like, basically anytime, you know, you are sort of reading some data from a file, you need to do one of two things. You have to know what the encoding is, so that you can interpret it correctly, or you need to discern it, which is actually what a lot of text formats end up doing. So Unicode actually has some sort of, I think they're called byte order markers, which basically are these like non-readable character, non-text characters, non-visible characters that tell you sort of something about the encoding. So a lot of text formats actually stick a byte order marker. Actually, I wonder if byte order mark. I wonder if what we're seeing at the beginning of this is a byte order mark. FEFF. No, that's not what we see there. EF does not look like a byte order mark. So in any event, you know, when a lot of times we don't have to worry about this stuff. Like if you've been doing web programming for a while, you have most likely run into weird like language issues, well, like weird issues with characters in different languages, where, for example, you have I remember, like, you know, various issues where like you would have like an Apache web server in front of a another like, you know, HTTP request handler, like a CGI bin program or something like that, where one where the CGI bin program would output the data in one encoding, and then the what's called Apache web server would be configured sort of incorrectly, and it would actually basically output junk. So then you get these like weird, like you go to a web page and it's like, it just looks like gobbledygook, like there's no like readable text. These are text encoding or just data encoding mismatches. And they happen a lot less than they used to. Even just like opening like a text file, you know, sometimes you used to open a text file and it'd just be like some junk, and it was like you didn't like it got like written to the wrong encoding or something like that. Nowadays, like, software is a lot better. So like we don't need to worry about this as much with text encodings. Also, like Python, for example, does a bunch of magic. So you can see when I opened this file, I opened it for write in a binary format, which means that it's actually not going to try to encode anything that goes into the file. It's just going to write the raw bytes. You can, if you omit this B, so you're just opening the file for write directly, by default it's a text format. And the text format that it's open depends on the system, like the encoding, like the Python default encoding, which in turn depends on the system encoding, but default encoding. But what that means is, like, when you're writing strings to a file, generally it's going to do the right thing and it's going to encode them as UTF-8. But you know, that whole there's been a lot of confusion, particularly in Python, around encodings and like how that all is configured properly. And I think in Python 2 in particular, because strings were just bytes, basically. Strings were not UTF encoded strings. They were actually just like they were sort of raw bytes that typically you would encode in your source code when you write, happy birthday Matt here. This is ASCII encoded, and because of that, the data would get written to the file as ASCII, and that would be readable downstream. But there was a lot of situations where, like, the data in your string would have been mangled at some point, and then you would just be outputting some garbage. But in Python 3, there's actually two types. There's a bytes type, which is an array of unsigned characters, or array of byte values. And there's a string value, and a string value is always UTF-8 encoded. Same with Go. So like the Go programming language has a byte slice or a byte array. And it also has like a string type, which is always interpreted as UTF-8. So Gabriel is saying, do you want to chime in, Gabriel?
Oh yeah, just making a point of database too. Like it's
Yes,
important to share
very
that
good point.
language and environment in the same encoding as your database, because especially in Latin America, where our languages have accents, it's very common for most of the things work, but accent and chars not be properly encoded, because like you said, most encodings treat ASCII chars the same. But then when it got to more complex chars, we got in problem. And then we don't realize that until it's too late and it's in prod and you lost data, or like it's misencoded. You need to fix that. So it's a pain to make sure that your entire environment from end to end is talking the same language, basically, and take care of that.
Yeah, it's a really good point. So databases are like a really common, in fact, I remember at YouTube, our database was encoded Latin 1 for a long time. And the Latin 1 character set. So you can see the Latin 1 character set, I think, has, does it have accents? Yeah, so the Latin 1 character set, the lower byte, or the lower 128 characters are, I believe, 1-to-1 with ASCII, but the upper 128 characters are have like a whole bunch of other characters with accents, that so that basically it could support more languages, like Gabriel's describing, like Spanish or Portuguese. Like Latin 1 supports those languages reasonably well, but if you have a Latin 1 string and then you try to render it as ASCII, you're going to lose all those upper characters, and only the characters that are compatible with ASCII, the lower 128 characters, are going to show up in any meaningful way, and all the others will be garbled. So at YouTube, the database was actually the encoding for the string fields in the database were Latin 1 for a long time. And switching that to UTF-8 was like a fucking nightmare. And there was like all kinds of crazy fucking encoding issues that crept in there, before switching to UTF-8, and then also during that transition. So Latin 1 is a very common one, and I believe was, like, for MySQL, I believe it was the default character set for a long time for string values or string columns, and that could totally bite you if you try to like stick some UTF-8 in there.
Is UTF-8 the default now for a lot of things?
UTF-8 is now the default for like a lot of things, which is what made which I think has eliminated like 90% of these problems. UTF-8 is like, the default encoding for strings that programming languages tend to use. UTF-8 is
HTML, like as a default, it's automatically set in HTML5.
Yeah, well, like oftentimes now, I think probably browsers, if they don't know any better, if they're not told what the encoding is, they may try UTF-8, first, as sort of an assumed character set. So yeah, UTF-8, and I mean, for the whole reason why UTF-8 took so long to become the sort of standard was performance. So both Latin 1 and ASCII are fixed with character sets. So that every single character in ASCII is going to take 100, or is going to take 7 bits to encode. For Latin 1, it's going to take 8 bits to encode. And so given some, chunk of memory, like say you have 1,000 bytes that is Latin 1, that the length of that string is 1,000, right? You can just, you don't need to actually like do any complicated like traversal of every single character within there to determine whether determine the length of the string. But UTF-8, that's not the case. UTF-16, at least my understanding of it was, actually maybe UTF-16 is also variable width, and it's UTF-32 that is fixed. That would make more sense. So in any event, UTF-8 and now I'm thinking about a UTF-16 as well are variable width. So you need to determine how long a string is. You need to actually traverse the entire string and say, okay, this character is 8 bits. This character is 8 bits. This character, is I forget what the term is, but there's like a term where like certain bytes or certain sets of or certain characters have a prefix and then they have a variable length suffix. So in UTF-8, that can mean it can be 16 bits or 32 bits. I think not 48 bits, but I could be wrong about that. But basically, you need to then stop and be like, okay, so this byte says that the next 3 characters are all part of this one, or the next 3 bytes are all part of this one character. And so that was like the argument forever, was just like, well, what about in the C programming language, everyone uses string length, strlen everywhere to figure out how long a string is. Well, does that mean that it's that many bytes or that is that many characters. And so UTF-8 like got kicked down, the can kicked down the road for years and years and years, because languages did not want to bite the bullet and be like, use some variable width encoding. So a little bit of history for y'all. Any other questions? We didn't even get into, I was actually going to like get into like binary encodings and other encodings. But text encodings is super important, and it's like a kind of a big topic. So any other questions about any of this stuff?
Can you have different encoding?
Sorry, go ahead, Lena.
Sorry. Just curious, can you have different encodings in the same file?
Sure, yeah, of course. So you can basically, well, we could probably do that here. So let's use our good old like encoded.bin, and let's take our string and let's encode this as UTF-8 and write those bytes to the file. And then let's also, well, let's do UTF-32 for fun. So let's just run this sucker and see what our encoding.bin looks like. Look at that, that is ugly. So let's look at what we have here. So first we have our UTF-8 string, which it's a variable encoding, like variable length encoding, but all of its lower 7 bits match, just like Latin 1, all of the lower 7 bits match ASCII. So when you're looking at UTF-8 and it only has, the English Latin characters, it will look like ASCII. So that's what you see here. Happy birthday, Matt. And then we started encoding as 32. I think this might actually be a byte order mark right here. Say, I think FFFE is a byte order mark. Or FEFF. This is interesting. So actually, FFFE. So I think what happened is this is a byte order mark. This is telling you basically, hey, this is actually some of what I told you was bullshit. So byte order mark is actually for the endianness of the data. So the byte order mark does not tell you what the UTF or what the Unicode encoding is. There's another thing for that text editor stick in there. But the byte order mark actually tells you the order of the bytes within the 16 or 32-bit frame that each character encompasses. So what this says is FFFE means that I believe it's big endian. FFFE. The bytes will be swapped. Yeah. So if the so FFFE means I believe that it's big endian. Oh wait, it's right here. The BOM will appear in the sequence of bytes as FEFF. No, but we're FFFE. So it's actually little endian. So for some reason I thought ARM, for some reason I thought that the ARM processors were big endian and that this would be big endian, but anyway, there's probably some other reason why. But in any event, this is basically telling you that, hey, the computer that wrote this data puts the, and I'm going to get this wrong, but puts the least significant, actually, I think for little endian, it's the least significant bytes first, and then the most significant bytes. And actually, you can see that here because the Unicode endpoint, I think this is little endian. Yes, okay, this is right. So the you can see that the like character H, if we get the ordinal value, which is the byte, like the unsigned byte integer value of how an H is encoded, it's going to be 104. And you can see that this 4 bytes is encoded as is 104, is interpreted as 104. This 32 byte, 32-bit integer value is 104. But the least significant byte is actually first, which is little endian. So in a big endian, if this were written in a big endian format, which also is the network, if you see like something referred to as the network byte order, the network byte order, so the byte order that computers communicate over over network protocols, is actually big endian. So if this was big endian, then this would be swapped, and the 68 would actually, well, it would be swapped twice. So the first 2 16 bits would be swapped with the last 2 16 bits, and then each byte within those would also be swapped. So this 68 would end up here where this 0 is, at the very end of the 32 bits. So sorry, tangent, but you can see like we have 2 encodings here in this file. So we have UTF-8 first, and then we also have some and then we have some UTF-32 as well. And if we try to open this sucker up in a text editor, well, it would look like nonsense, because it's like, okay, this looks like ASCII or UTF-8 or something. And then it's like, oh, but what the fuck is this? I don't know. So that's why you get nonsense.
Thank you.
Does that answer your question, Lena?
Yeah.
It's not a good idea, but you can do it. And like if you were actually going to do that, if you were writing a whole bunch of strings and they were in different encodings to one file, you would probably put some kind of like prefix before each string that tells you the encoding or something, so that you can actually just make sense of it.
What's the advantage between like little endian or big endian in terms of like when to decide? I know that we as programming, like end users of programming language, we rarely will need to decide this, but like when people are doing infrastructure work, what's the difference between those? Like, is it performance? Is this like oriented to being easier to identify some stuff?
Well, little endian is basically a legacy of, I believe it's basically a legacy of the Intel architecture. So it doesn't matter. I mean, at the end of the day, like a 32-bit in a 30, like say in a 32-bit Intel processor, you will like the actual, and we would have got into this if I talked about assembly, but like the place where all the operations happen in a CPU are called registers. And so what happens when the CPU needs to do some work, like adding two 32-bit values, it will generally copy those from memory into registers in the CPU. And then that's basically, the registers are just like super fast, like access, you know, very, there's very few of them in a processor, but data access from a register is super fast, and you can do, like, the CPU actually can do operations on the things in those registers. So what you typically do is like, you know, copy some information into the registers, say add, and the CPU will actually like perform the addition. And an Intel processor actually like is just wired differently, right? So it's like the add is wired in such a way that like the add operation is wired in such a way that like the bits get added properly in a little endian interpretation of those numbers, right? So so it's just the way the CPU is wired. And I don't think, I'm fairly sure that ARM is ARM processor, or like ARM processor endianness. Endianness in ARM. Big endian have, yeah, so I think ARM processors are big endian generally, although I think also that many CPUs can switch. So it says something about like endian modes, and I think maybe like that's something that certain processors can do, is actually switch between. So in any event, there isn't really a performance difference unless you're trying to do you know, high performance operations on very large streams of data that are in an endian format that is like the endian format that is not the one your processor can handle. And I think there's also like certain benefits, like in terms of like CPU design back in the day, like it was probably that it was just like a little bit easier to do certain like computations, certain kinds of computations on little endian versus big endian, just the way that, again, like the way things were wired. So, which is probably why Intel chose little endian at that time. The big advantage of big endian in this day and age is that it is the network byte order. So when two computers are interchanging information, it will always be in big endian. So that just means if two big endian computers are communicating, there's like slightly less, you know, computation that has to be done to like shuffle the data around correctly.
Cool. Yeah, that makes sense. Thank you.
Yeah. Any other questions? Who knew that one could ramble for 50 minutes about this shit? But I guess there's a lot there. All right, thanks everybody. This was fun.
Thank you.
Thank you,
Thanks,
Dylan.
Dylan.
Thanks, Dylan.
Thank
All
you.
right, bye-bye.
Bye.